All right, guys, welcome back again. So, the last time we stopped in class, we were talking about the mean and the variance, and we'll talk about different distributions under each of the category of discrete and continuous. And we also talk about the importance of expectation and how we can use that to get our mean and our variance. We look at several examples like the Bernoulli, the binomial, and also the normal distribution. And we said there are so many other distributions that belong to both categories and how we can use expectation to get their mean and variances. All right, so we are going to move on to talk about the R code. How do we set up R code to compute the mean and variance? It's very funny because you only need about one line or two lines of code to do the workings that we had the other day, and this is how the setup looks like. Of course, you have to set your seed for reproducibility. You have to pick the function for that distribution because each distribution has different function. So we have to be very careful of that. So this is saying that this is generating a 10,000 sample size from a binomial distribution with size equals to 1 and probability is zero point 0.3. That's about 3 over 10, right? And also, we want to compute the mean and the variance. This is something we can solve manually. But let's go to our hard code and show you how we are going to get that result. Okay, so when we move to hard code, this is what we're going to be having for the expectation and the variance. Let me clean my global environment first of all. Okay, so if I set the seed and then I run this, I am going to have the mean to be zero point 0.3 or the variance to be 0.21. You can solve this and remember the variance of a binomial distribution is what? So remember, I set this to be R binom, but I picked the size to be 1. You guys should have questioned me. How sure am I that the size is 1? So it's a Bernoulli. This is a Bernoulli. This is not a binomial. When we set the size to be 1, that's the default of switching from a binomial to a Bernoulli. So that's why when you use your variance, it's going to P into 1 minus P, not NP into 1 minus P like we discussed. So now you should ask me, what if we want binomial? How do we set the size? Come to the description here. Number of trials. The size is talking about the number of trials. When we put the number of trials to be 1, that makes it a Bernoulli. But let's say we change it to something else. Let's say we are doing the number of trials 10 times. Now, be careful of this 10,000 that you see here. This one is generating the number. It's talking about the total observations that you have. It's not talking about it's not talking about the trials. How many times are you doing it? Let us be careful of that because I'm sure some you might probably get it confused. This word is talking about the total number of data that you have. It's just like when you do a die. When you do a die, you can only get one, two, three, four, five, six. There are some experiments that maybe you have to do it. Maybe the total sample space is about 10,000. It depends on what the experiment is, right? And in this case, we are generating 10,000. But how many trials, how many times are we going through what we are going through, right? That is the size. The size is talking about the number of trials. It can be 0 or more, okay? And we already know that the size for a Bernoulli can either be 0 or 1, right? But if it's a binomial, it can be from 0, 1 to n. Let's not mix that up, okay? So when we pick 10 here, this is what is setting it to an R binomial. This is what is setting it to a binomial distribution, okay? So, and we already picked the probability of our success, which is what? Zero point 0.3. So it's saying for each of the trial, the probability of success should be 3 over 10 or zero point 0.3, right? So when we do that and we run this code, you can see that we got a different value. In fact, the mean is about 2.9, while the variance is about 2.12. Let's be careful. This is talking about the mean. Before you say the value is wrong, this value is right. The mean can be greater than 1. The variance can be greater than 1, okay? The mean is talking about the average. Remember, we are not calculating the probability in this case. We are only calculating the mean and the variance. So that's very important, and I needed to clarify that carefully. So let's go back to the notes. Okay, so the next thing we'll be doing now is let's talk about common distributions that we have in R. We talk about binomial for this presentation or for this talk or for this class. We are restricting it to certain distributions, but we're going to give you a cheat sheet that you can see all distributions or possible distributions. All right. So we have a binomial distributions, we have a normal distributions here, and then we have a uniform distributions. Okay. So for a binomial distribution, let's go back to our notes. First of all, you have to understand. Now, let's talk about binomial distribution. So, for a binomial distribution, let's pick a pen. Okay, so let's say we are talking about distributions, right? So, if we are talking about distributions and we pick a binomial, remember, binomial is coming from what? It's coming from a discrete. Is a discrete distribution. It's not a continuous. And it's because it's coming from a count data. When you do an experiment and we say, oh, how many times we are doing this experiment? It's coming from a count data, right? You can call it like it has a finite number of trials that you can do it. Let's say you want to do it 10 times, you want to do it 8 times, you understand? So that's what makes it discrete. I'm trying to be careful of that counts because there's a distribution that is strictly connected to count data, like a Poisson distribution. But anyway, for binomial, it's saying for a finite sample size. Okay, so now the first thing we need to understand is what is the probability mass function of a binomial. So we can say P of x equals to x is going to be what? N of x, p raised to power x, 1 minus p, n minus x, where your x is coming from what? 0, 1 to what? To n to n. Okay, this is very important. This is the probability mass function of a binomial distribution. Your n is talking about what? It's talking about the total number of trials. Now, x is talking about, let's say the n is talking about the sample size. The x is talking about the number of trials. The probability here is talking about the number of success. And the 1 minus p is talking about the probability of failure. So, I said it earlier that q can be 1 minus p, and it's representing what? Probability of failure. Okay? N is sample size, X is trial. So from here, we can generate our mean and our variance, like we said the last class. The expected value of X in this case is summation X, P of X equals to X, and the range of X. So you can do this and substitute. In fact, this should be an exercise. And from here, if you properly do your math right, your expected value of X should be what? NP for a binomial. Okay, that's something very interesting and I love about statistics because I already know the mean and the variance of most of my distributions. So if I have to prove to get to that mean, then I just know that I need to play with the mathematics around it because I know where I'm going. Okay, so that's something you can do as an exercise. Substitute this px into this and open it out. You have to do some operations to be able to arrive at this mean, but you will if you carefully follow the procedure. And of course, if you're having any struggles while doing that in any of our office hours, we can talk about it and even solve them if you really want us to do that. Okay, but for the purpose of restricting the class notes and also, of course, to make it easier for people when you are going through this who will not go into the proving part because that would be too much. All right. So the same way we can get the mean, we can get the variance. And we said the variance of x is going to be what? MP into 1 minus p. Okay. So if we do that for binomial, we can get the mean and we can get the variance. Okay. So we also have some other distributions like the one we talk about, like the uniform. Uniform is another special distribution. So now if you want to write a binomial distribution, how do we write it? How do we show that a particular distribution, a particular random variable is distributed to binomial? So when we say x is distributed to binomial, some people can write it finish, some textbook don't write it finish. So it takes two arguments. So that's the mean and the variance. What's the mean that we discussed? We said is what? Is MP. And what's the variance? We said is MP into 1 minus P. Okay, so that's what binomial takes. Oh, sorry. I think I mixed that up. Okay, so it doesn't take the mean. It takes the two. So we have what we call kernel, and then we have what we call we call it the argument or the function. So I think that's where I get this part a little bit mixed up. So this is n distributed to binomial. We talk about the parameters in this case. What are the two parameters that we have here? You can see we either have or n or we have P. N is the sample size, P is the probability of success. So this is how we write the argument of binomial. So we're going to take this part out, okay? So this is taking the mean and the variance. But when we are writing the binomial distribution, we don't write it in terms of the mean. We write it in terms of the parameters, okay? So that's something else that we have to notice. So if we go back to our class notes, the same thing applies to the rest of the distribution. So like by default, you can see that the normal distribution takes the mean and the variance, but it doesn't necessarily mean that every other distribution must go through the mean and the variance. It takes the parameters, and these are the unique parameters that we have in there. And of course, for the uniform distribution, it takes the minimum value and the maximum value. The minimum value in this case is the A and the maximum is B. Now, if you notice when we were doing our functions in R, we were using R, is either we use R binom, R norm, R unif, because we were generating data. Because at DP we have our data already prepared, we won't have to use the R generator to generate our data. But we're just saying that we have other functions in R that perform different operations. If you use the D, it is either for the density or for the PMF. Remember, we already talked about binomial. So if you want to calculate the density function, we can use D norm, we can use D bind, we can use D unif. So if you want to calculate the cumulative density function, now, there's another main axioms that I did not talk about in the last class. Let's say we are talking about okay, sorry about that. Okay. So when we talk about the axioms, there's another axiom that we call it for proper, we call it proper we have proper and improper properties. So for proper, it's saying that when you integrate f of x dx over the range of x, it must be equals to 1. We call it cumulative density function. It's saying that when you, it's just like when we say the sample space in the other time. When we say the sample space, we say the sample space must be equals to 1. That's what the cumulative density function is also doing. It's saying when you integrate the probability density function on when you cover the entire range of that distribution, it must be equals to 1. It's just like when we have uniform. Uniform distribution, when you integrate from minus infinity to infinity of 1 over square root of 2 pi sigma square, right? Into what? Exponential minus 1 over 2x minus mu over sigma square, right? Then you do dx. This must be equals to 1. It is a major property in the probability. When you integrate over the range of that function, it must be equals to 1. Okay, so and also for quantiles, we also use quantiles in probability and also the R function for generating numbers like we did, especially when we start simulating data, which along the line we're going to talk about that. We'll properly dive into some of these things in details. All right, so the next thing will be binomial distribution. So we have a specific example on binomial distribution and we show you how you can solve manually and how when you use R you are going to get the same result, of course. So let's say we have a random variable that is distributed to binomial of 3, 6. So we're saying the sample space should be 3 and then we said the probability should be 0.6, and they want us to calculate the probability mass function of that. So for us to do that, we need to sum across. So we say probability of x equals to k. Let's say k is the number of trials in this case. And then we try to show that our k can take a value from 0 to 3 because the sample size itself is 3. So the k can start from 0, it can start from 1, it can start from 2, and it can start from 3. And of course, when we come here, we are going to substitute them individually. We can go back and try to do maybe 1 or 2 of this to even make it easy, but it's still the same thing here. So when you substitute across, you are going to get their corresponding value for when k is 0, for when k is 1, for when k is 2, and for when k is 3. And when you try to check that particular axiom that we talk about, that when you integrate across all the possible ranges of the PMF, you are going to get 1. When we check, you can see that it is 1. And we can do the expectation by using the n times the probability of success, and also the variance by typing the product of the sample size and probability of success with the probability of failure. Okay, and so we can also do the same thing in R. See how much effort we put in. Imagine if we have a larger settings, it's going to be a lot of work to find their probability. So we can use some of these functions that we talk about, like the D norm, like the D binom, like the P binom. Okay, so we just need to set our size. We have the algorithm, we have the arguments. Let's go into R and understand that better. Okay, so when we come to common distributions in R, now, the first thing, if you come here, you can look at, in fact, we already have everything here. We have the D binom, right? We have the D binom, we have P binom, we have Q binom, okay? And we have the R binom. So in this case, because we are doing a PMF is probability mass function. In fact, there are some people that call it probability density function. Even though we try to distinguish between PMF and PDF, we say PMF, we use it for discrete, PDF, we use it for continuous. But like the R generator, it sees even PMF distribution, it takes the density form, okay? So you can call it a D binom. What's the first thing is going to take? What is the size? How many trials are you going to do? So in this case, we are taking our trials from 0 to 3, right? So you generate a sequence of your trials that is coming from 0 to 3. And then we set our sample size, which is to be 3, and then our P, which is the probability of success, to be zero point 0.6. So we use our PMF. We said the CDF. What does the CDF does? It does the cumulative density function. It integrates across all those possible values and it gives you a value. Okay, so when we do that, what do we have? We get our P. What do we get? So you look at different cases of K and you look at the corresponding PMF for each one of them. Now, something very interesting is in CDF, you can get your CDF from PMF, right? So you have 0, 1, 2, 3. Once you have gotten your PMF like we have here, right? The next thing will be CDF will take the first value of PMF. You can see we have 0.064. The next one is going to cumulate the first two, is going to cumulate 0.064 and 0.288 together to get the next one. And then you do the same thing again for the next one until it stops. So that's very interesting. And then the next thing we can do is we can find the mean and the variance. That's what we have here. So we find the mean and also the variance. So that is something you can practice with different distributions to be able to compute this on your own, and so that when you see other distributions that you have not been used to, you will understand that. Okay, so the next thing would be, how do we simulate? Earlier I talked about how we simulated about 10,000 variables, and then we set our trial to be, I think, 1, and that was for a Bernoulli distribution. Okay, so when we set our seed, it helps us for reproducibility. We set our sample size, and then after that, this size is talking about the number of trials, not the number of sample. Okay, so the size here is 3 because this is how the argument is in R. So we have to understand that. And we use this generator to indicate that it's coming from a binomial distribution, and we also indicate the probability of success. And we can do some empirical probability just to understand by using the function table, and we can compare the mean and the variance. Okay, so when we do that, we can also do the same thing for different cases. In fact, we can see the behavior of a binomial distribution with different arguments and see how that works. Let's go back to her and see this beautiful plot, because I'm sure it will be beautiful. Okay, so when we run this code, what do we have? When we run this, what do we have? We can see how the Instagram behavior. Let's say this one first. So this is showing the density of the binomial distribution that is coming from a sequence of 0 to 10, and then it's showing the size of the number of trials is 10, and then the probability is zero point 0.5. Okay, so when we look at this, these are the numbers that we've generated, right? So the PMF is like this. If you want to do the PDF, what do? You just use the function for the CDF, right? So, and the function for the CDF is what? Is the Q binom. Is it? Yes, yes. Okay. So we can come here in case you want to forget, because I forget, but that's why we have this. So when you come here and you indicate that, we can use that to compute the cumulative. All right. So we try to visualize to see the behavior, if our distribution is normally distributed across what we have generated. And if you look at this, it is normally distributed, because if we try to plot like a density graph, we can see that this is symmetric, it is bell shaped. So we can say it is normally distributed. Okay. So another thing now is we can move on to the next part, which is um law of large numbers. Why do we talk about law of large numbers? So law of large number is very interesting because it talks about the convergence of our distribution. It tells us how our distribution can converge as our sample size increases. Take for instance, we talk about the sample mean. Now we want to understand how can our sample mean converge to the population as we increase the sample size. Okay, remember that when you express the sample mean, it is 1 over n summation x, right? And it will converge to the true mean. Now remember, when we talk about the basic of statistics, let me go back and remind you of the first thing we did here. We talk about the paradigm around statistic. We said we start with a population, and then from the population, because it's very hard for us to estimate the entire population. It's very hard to understand the whole parameter around the population. So we are selecting a sample from that population. We want to use our sample to understand our population, and we want to use our sample to generalize on our population. Okay. So when we have this sample, we use a probabilistic model to select appropriately, and then we use the inference on the sample to be able to talk about the population. That is what we talk about. So at the end of the day, we want to understand, the more you increase the sample, you are already tending to the population. You remember, we only selected few. So if I keep increasing my sample, what happens? I am moving towards understanding the population, understanding. So like the population, it uses what we call a population parameter. A sample uses a statistic. When you increase your sample, you're already going back to this. So that's what the law of nudge number, that's what it says. And we can demonstrate that in the R code, okay? So we can also, how did I go back again? Okay, all right. So yeah, so we can also do that by visualizing how this looks. We imagine having about 10,000 sample. That is a large sample enough. So we can see how the law of large number converges. Let's go to our hard code and demonstrate this quickly. Okay, so when we do this and we run this code, in fact, you can do it for other distributions. Look at that. Look at that. So this is what this shows, that as you increase your sample size, your distribution is going to converge to the population mean. I'm going to leave you with the rest of the code to practice, and then we can talk about some of these things in our office hours. All right, guys, I hope that you guys have a great day. We have a practice problem that I would want you to practice. If you're having any issues, this is something that we can talk about. And most importantly, our cheat sheet. You guys want to forget? We talk about the four standard prefix in distribution: the density, the cumulative distribution function, the quantile, and the random generator. And we talk about how our binom can help us to get to Bernoulli by just specifying the size to be 1. Okay, and then these are all the distributions. We have the distributions for the normal, for the uniform. How do you write each one of them? This is for continuous, and this is for discrete. So I want you guys to explore this properly, and see you in the next class. All right, have a great day. Bye bye.